Buongiorno. My name is Tobias Nyholm, and I'm going to talk about Dynamic Programming 101. There's my Twitter handle, so if you want to harass me for the next half an hour, you're free to do so. And I want to give this talk because I believe web programmers, they only care about echoing out HTML as quick as possible. I want to show there is more to programming than just printing things really, really fast. So, short about me, I work at happy.com. We match people and companies on the soft skills. I do plenty of Symfony stuff, and I'm running the PHP meetups in Stockholm. I'm also doing plenty of open source stuff. I started my open source journey in 2016 when the PSR 6 came out. So me and my friend, we built some bundles for, we built some implementation for PSR 6. And at the same time, I started doing HTTP plug, which is basically an abstraction over HTTP clients. And when you're doing abstractions, you obviously can do a lot of API clients and a lot of mail clients. And then I'm running both Guzzle and Buzz. I'm maintaining both the libraries. And I do a lot of PSRs and writing my own PSR, and I do testing and some geocoding and stuff like that. My real favorite one is NSA. That library totally violates all class privacy. So accessing private properties and methods is no issues with NSA. Nevertheless, get started. Whenever you got a problem, you instantly started thinking about how can I divide this problem into smaller problems. Say the problem of getting to work in the morning. You think, you don't really know the solution to that already. You think, hey, how to get out of bed, how to get dressed, how to get some coffee, how to drive to work and stuff like that. So you have all the sub-problems and you divide them into further sub-problems. Same thing when you're building a website. If I say you should build a website doing whatever, you first think of, hey, what's the design going to look like? How's our data models going to look like? And then when you figure out the data models, you maybe think about, what is the persistence layers going to look like, etc., etc. And this is called divide and conquer. And as you all are programmers, I know that there's nothing new for you. You know all these things. And you do it in your head automatically. And whenever we talk about divide and conquer, you may think of recursion, right? And if you don't know recursion, this is a simple example of it. In my example, I'm calculating factorials. Factorials is basically 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. You all know factorials? Excellent. This is a iterative function, and that's a recursive function of it. A recursive function just calls itself. So if we want to use a recursive function, we got to come up with a great idea. We got to figure out that 4 factorial is actually 4 times 3 factorial. And when we know this, it's easy to write this function. And I don't know, if you studied computer science, it's a law saying that you cannot talk about recursion without mentioning Fibonacci numbers. You nodding? Yeah, sure. Fibonacci was a mathematician. He lived 1,000 years ago. And he on his free time, he came up with a sequence of integers because he liked integers. And so this is guy inventing Fibonacci numbers. Fibonacci number was not invented by the Da Vinci Code, nor Leonardo da Vinci, as a guy who applied for a job at me once told me with great confidence. And anyhow, the Fibonacci sequence is pretty simple. Here's the first 17 numbers, and the second line is just the index. So to calculate a Fibonacci number, you take the sum of the 2 previous Fibonacci numbers. Simple as that. And in code, it may look like something like this. So we have to realize that this is a recursive function. So Fibonacci for 5, it's actually Fibonacci for 4 plus Fibonacci plus for 3. And this is what it looks in code. And this is what it looks in math. It's pretty simple. So what if I ask you, what is the 15th Fibonacci number? 610. It's easy, we just looked at the list. What if I ask you a little bit more difficult question? What is the 1002nd Fibonacci number? I just assume that you're all saying it's a very, very large number, we don't know. It's actually so large it wouldn't fit on this slide. But what if I told you that the 1000th Fibonacci number and the 1001st Fibonacci number were x and y? What is the 1002nd Fibonacci number? X plus y. So, if we know the solutions for two simpler problems, we can easily calculate our difficult problem. I want you to remember a lot of things, but remember this specifically. Let's go back to Fibonacci again, the recursive function we had. If we started this easy function, and we started with an example, we say if you do fib5, we quickly realized that fib5 would actually generate two new calls to fib4 and fib3, which in turn would generate even more calls, which would generate even more calls. So we're having all this messy call stack here. And if we study our call stack, we'll see that we actually called fib2 more than once. So what if we come up with an idea, say could we cache this? Could we save the result for fib2 so we don't have to do the massive calculations again? And this is just simple caching. And in computer science, we may call this memorization. So I added a class because it looks prettier, and I very much the same function, but I used a cache. Is this obvious? Excellent. So last time I did this talk, they said, hey, great talk, but what is dynamic programming? So I added this slide. Dynamic programming is basically you have to divide the problem into overlapping subproblems and use that knowledge to reduce some calculations. So if you expect dynamic programming to be like code writing itself, you were wrong. This is pretty much it. So let's go back to this code stack again, seeing this is all the code stack without memorization, without caching. And if I add caching, there's a lot less calculations. So that's why with memorization, this is way quicker. I like to flip back and forth because I'm going to see it's way quicker. So this is pretty much the hello world of dynamic programming. I wanted to go to do more fun stuff. And fun stuff is obviously graph theory. The very, very first thing you need to know about graph theory is that these are not graphs. These are charts, these are diagrams, these are whatever. They're not graphs. A graph has a node, and a little bit more complicated graph has two nodes. And there's connecting nodes, there's an edge. An edge can either be undirected or directed, and it can have a weight on it. This is the basic of graph theory. I assume you all know this for now. And a little more complicated graph could look like this. This could represent computers in a network. It could represent persons and how much, and if they know each other or not. And if you slap on some numbers on here, it can represent persons and how much they like each other. Or it can represent cities and the distance between the cities. So let's go with the ladder analogy. Say I have a point A and B. I want to discover the quickest way to get from point A to B. Of course, we can study this graph and we can do some calculations and additions ourselves to figure out what's the shortest path. Or we can have a strategy, or as we like to call it, an algorithm for doing this. And an easy algorithm to go to is a breadth-first algorithm. Have you, show of hands, do you know of this graph theory and breadth-first algorithm and stuff like that? Not like a third of you. Okay, so I'll go on. A breadth-first algorithm is basically we go for our first node, and then we look at all our neighbors, and then we write the cost to getting to that neighbor in the circle. And then we take another leaf, the number 5, and discover all its neighbors. And then we continue on with discovering neighbors. And I don't know if you saw this. See the 5 in the middle was first an 8, and then we find a quicker way to get there, so we rewrote that. And then we continue doing this, and when we discovered all the graph, we can easily We have the number, like 12, those the cost 12 units to get from A to B, and we can easily backtrace to show the shortest path. I would like you to consider this matrix maze. It's the number in the maze, the number in the square says how expensive it is to get to that square. And you can only travel up and down and up, down, left and right. You can't go diagonally. And you can see how this easily can be converted to a graph, right? Okay, I'll tell you, this can easily be converted to a graph. And I use this representation because I think it will be even more evident what I'm trying to explain, and I think it's easier to make this as well. So our task is to navigate from start to goal and find the quickest way. And I slap on some colors here to show, the colors represents the number, basically. So we do the very same thing again. We do a breadth first algorithm, and as we go, we write down the cost of getting to each cell. So if we start with number 3 here, the start node, we write down 3, 0, the coordinates, and the cost to get there is 3. Then we continue with all its neighbors, and discovering its neighbors, and we continue to write down the cost to getting there. And this is basically the breadth first algorithm. Like, I'm starting with my nodes, discovering all my neighbors, then go to the first discovered node and discover all its neighbors. You see the pattern? You could speed this up by using a multiple, a dual breadth first search. So you start both from the goal and from the start, and then when they find each other, you have found the shortest path. As an alternative for breadth first, there is depth first, which basically does the very same as a total search, but it goes one direction and then continues that direction until it finds the goal. And then it steps back a little bit and then you continue that direction. It's also have this list of values that it keeps in memory. And as you see, it also searches the full graph. Both breadth first and depth first search the full graph. And we think, can we do better? Let's have a greedy algorithm, an algorithm that only, whatever stage we are, we take the best possible decision. So let's start with the 3, and the best possible decision of its neighbors is obviously 1. And then there's another 1. We're feeling pretty lucky now because they have found a really short path. And I've been really tricky with designing this maze, because here is just a pain of eights. So this greedy algorithm wouldn't do very well here. This greedy algorithm is called the best fit algorithm. And oh, sorry, I don't know if I said this, but this is not only mazes we're trying to solve these algorithms and problems. We solve any kind of thing you can represent with graphs. So this best fit works pretty awful in my example. You could also do worst fit, which takes the worst possible decision, or you could do like a random walk. You just randomly decide where to go next. And believe it or not, these 3 algorithms, there's no preferred choice. Depending on your scenario, your data, then you can choose algorithm. But in the average graph, there's no preferred choice. This obviously doesn't search the full graph, and also you have to have a way to figure out how to handle loops. But this doesn't search the whole graph, but it doesn't really find this quickest path. So let's try to use our newly found dynamic programming skills to have another algorithm. It's called Dijkstra's algorithm, which is a dynamic programming algorithm. Have you heard of Dijkstra before? You guys who raised your hand of breadth first. You all liars. You haven't heard of breadth first, but have heard of Dijkstra's. Anyhow. Dijkstra's algorithm, I'll show you the example. You start with the start node, and you say, how expensive is it to get here? You write that down somewhere. And then you visiting all your neighbors. You write the cost for getting to neighbors. And then you see, and now you marked number 3 as visited. And then you go for the next discovered node that is unvisited and with the lowest value. That's the top left one. It's discovered, we haven't visited yet, but it's discovered and the value is 4. So we go to this node and we discover all its neighbors. And now we go to the next discovered node that is not visited, that has the lowest value. It's this one. And discover all its neighbors. And I want like add a 7 here, but since 5 is lower than 7, I don't add anything, so I just remove that error. And then I continue on. You get the gist? Yeah, now it started by running by itself. So compare Dijkstra's with the other algorithms I showed you. This will guarantee me to find the shortest path, and will also it won't search the full graph. This actually my graph is a kind of poor example, but eventually it will show you that there's some nodes that haven't been visited, but I'm still guaranteed that I have the shortest path. I'm just going to mark the last one as discovered. So these nodes have not been visited. And I know with this example, it's quite hard to... I think it's hard to see that this is a dynamic programming algorithm. So I wanted to do the very same thing, but in a different notation or different animation or whatever. So I'm still going to start with number 3, and I marked number 3 there. And then I'm discovering all my neighbors. And now, this is a smart thing. This is what I like the most. I use this problem instead. I had a 30 squared matrix, but now I have 3 problems with a 29 squared matrix, and I just add a constant to the solution. So I had a very large problem of 30, but now I have simpler problems of 29. And if I continue with this, now I have a 27 squared matrix, and that's super easy compared to the 30 squared matrix, right? So I had my big problem.
We are searching for a buffer.
Okay. I'm using this. Do you hear me better now? So to connect this with Fibonacci, we realized that to solve fib 5, we use the solution of fib 4, right? And to solve the 30 squared matrix, we use the solution of the 27 squared matrix. And if you want to do more math, we could slap on some math here. With this math basically says that if we have these 6 nodes and we're going to find the optimal path that may or may include some of these nodes, we can solve this problem by finding the optimal path of B to F with adding A or not adding A. Do you get me? And if you have even more math, you can say something like this. We know the optimal path is between I and J. That's a fact. And the node before J is K. So it's easier to find the optimal path between I and K and then just add on J. It has been a lot of math, there have been a lot of arrows, there have been a lot of theory now. So let's take a pause from this for a moment. And I'll tell you the hardest way to get $1 million. I gotta mention big O, the big O notation. It's a way to measure time complexity. And it's basically how long it takes to run an algorithm. And using the algorithms we've seen, the 4 algorithms we've seen are these. These are all linear or almost linear. Dijkstra's algorithm has a worst case of n log n, but has a way better average. That's why it's preferred. But this is a pretty simple problem, just to find the shortest path. Say that we want to have a more difficult problem. Say if you have a bunch of cities, you want to visit them all and find the shortest path between all the cities. This traveling salesman problem, or TSP. The best possible algorithm we got for that is Bellman-Held Karp algorithm, which has the n to the power of 2 times 2 to the power of n complexity. And if you don't know how awful that algorithm is, or how awful that complexity is, I have a chart for you. As you can see, there's no axis, so you can't really tell if I'm right or wrong. But having factorial or exponential complexity is awful. That's a super slow algorithm. And if you want to win this $1 million, you have to consider there's 2 groups of problems. One group of problems that we can only solve with difficult, hard, slow algorithms, and there's another group of problem we can only solve by
we can solve by quicker problems, quicker algorithms. And if you want to win $1 million, you have to either prove or disprove that these are two separate groups. So what I'm basically saying that if you can find a fast algorithm to solve traveling salesman problem, then you're rich. So why do we spend so much time talking about TSP? I can tell you that TSP is one of these NP problems, these super hard problems. And I can tell you there's a way to convert a hard problem to another hard problem. You can do this fairly quickly. Another hard problem is called integer factorization. I'm not sure how much security protocols you read, but most security protocols start with, hey, select two super large primes, and those are your very much secret primes, and multiply them together. That's your public key. So if you have a public key and you integer factorization, then you can have breached your security. But because integer factorization is so hard, you can't really do this. So what I'm again saying, if you find a quick algorithm for traveling salesman problem, you can efficiently brute force all our security in our society. You can also cure cancer, but who cares about that? Another super hard problem is the satisfactory problem, which is the problem Composer is solving for you when you do Composer update. This is a bumblebee. It weighs about 1/10 of a gram. And researcher has shown that if you have a beehive and you have different flowers, the bumblebee wants to visit all the flowers and then return to the beehive. And the bumblebee always picks the shortest path, which means that bumblebee solves TSP. Even if you remove one flower, the shortest path will change, right? And the bumblebee figures this out. So the bumblebee, I'm throwing out the rhetorical question now. Is a bumblebee smarter than a supercomputer? It solves TSP. Whenever I faced with a really, really hard problem, and my teachers at universities claim like, hey, there's no good solution to this problem, I feel, hey, I want to try. I want to do this. So let's try solving TSP and let's try to do it together. And TSP is super hard. I won't show any numbers, I won't show any math. I just show you the concept. So let's consider this TSP problem of 5, super simple. And now I gotta calculate a path to do. So I select the beehive, the H, and I have 5 options. Sorry, I have 5 options now. I select the beehive. Now I have 4 options for my next route. Now I have 3 options, 2 options, 1 option, and then I have 1 path calculated. Now I gotta change my choices a bit to calculate the second path. And as you may notice, this has a n factorial time complexity, because I have 5, 4, 3, 2, 1 options. And I don't know, I had a very poor sense of how n factorial works. So n factorial for 5 is 120. So there's 120 different solutions here that I have to calculate to figure out the best answer. N factorial of 15 is 1.3 trillion. Which means with this algorithm, my computer cannot solve a traveling salesman problem of 15. There's too many things to try. So let's use our newfound dynamic programming skills and try to do things a little bit better. If we consider this TSP5 and we consider all its subproblems, and then we just store the calculation for the subproblems. So let's consider this subproblem, let's consider this subproblem, and calculate the result of this subproblem, and the other subproblem. And I missed plenty, but you get the idea. Then we actually have and then we have calculated all the subproblems. We can actually have an algorithm that is the Bellman-Held-Karp algorithm that solves TSP in n 2 to the power of n times n to the power of 2 complexity, which may feel like, hey, this is awful as well. And you're right, it is awful as well. But with this algorithm, I may be able to do like TSP of 30 on my computer. And also, the Bellman-Held-Karp, This is the same Bellman as in machine learning Bellman, the one who figures out all the good math and death by dimensionality thing. So, this is great, this is cool, but we're just building website, we just print HTML, right? If you work in a company that's just, you do WordPress or just wanna show company presentations, this might not be for you. But if you do something cool, which I believe most of your companies are doing, if you do something cool like you're trying to show the best restaurant, or matching people and companies like I am doing, or maybe you are gonna figure out a score on an image somehow to show the most popular images somehow, then graph theory and graph algorithms will be super interesting for you. And also because you don't have to just solve the problem yourself, you can just convert your problem to a graph problem, and the solution will already be there for you. And by using dynamic programming, your algorithm will be way faster than they were before. Thank you very much.